Have you ever looked up at the night sky and felt a sense of wonder? The stars seem so far away, almost unreachable. The nearest star to our sun, Proxima Centauri, is over 4 light-years away. That means even if we could travel at the speed of light, the fastest speed possible in the universe, it would still take us more than 4 years to get there. Our current spacecraft would take tens of thousands of years for such a journey. It's a vast, almost unimaginable distance that separates us from the rest of the cosmos. This immense scale of the universe makes interstellar travel seem like a distant dream, a challenge for future generations far, far away. But what if there was a shortcut? Imagine you could fold the fabric of the universe itself, bringing 2 distant points right next to each other. Think of it like a piece of paper. If you want to get from one end to the other, you can draw a long line. Or you could simply fold the paper in half and punch a hole through it. This hole is a direct path, a tunnel connecting 2 separate locations. This is the incredible idea behind a wormhole. This concept isn't just something from science fiction movies. The idea of wormholes comes directly from one of the greatest scientific theories ever developed, Albert Einstein's theory of general relativity. Einstein showed us that space and time are not separate things, but are woven together into a single fabric called space-time. He also showed that massive objects like stars and planets can bend and warp this fabric. Imagine a large, stretched-out rubber sheet. If you place a heavy bowling ball in the middle of it, the sheet will bend and create a dip. Now, if you roll a small marble nearby, it won't travel in a straight line. Instead, it will follow the curve created by the bowling ball, spiraling inwards. In 1915, Einstein published his theory of general relativity, providing the equations that describe how matter and energy curve space-time. Just a few months later, a German physicist named Carl Schwarzschild found the first exact solution to these equations. His solution gave us a mathematical description of what we now call a black hole, an object with gravity so strong that nothing, not even light, can escape once it crosses a boundary called the event horizon. But Schwarzschild's solution contained something else, something deeply strange and unexpected. The mathematics seemed to describe not just a black hole, but also a white hole, a hypothetical region of space-time that you can't enter from the outside, but from which matter and light can escape. The term wormhole itself wasn't coined by Einstein or Rosen. It came much later, in the 1950s, from the American theoretical physicist John Archibald Wheeler. Imagine a worm crawling on the surface of a large, shiny apple. The worm wants to get from the top of the apple to the bottom. It could crawl all the way around the outside, a long and time-consuming journey across the curved surface of the apple's skin. But there is another option. The worm could, instead, chew a tunnel directly through the center of the apple. This tunnel provides a massive shortcut, a direct path from the top to the bottom that is much shorter than the path along the surface. This tunnel is the wormhole. For decades after Einstein, Rosen, and Wheeler, wormholes remained largely a theoretical curiosity. They were fascinating mathematical objects, but the consensus was that they couldn't actually exist in the real universe. The main problem was their instability. The Einstein-Rosen bridge, for example, would pinch off and disappear in an instant. Even if one were to form, it would be utterly useless for travel. Any traveler attempting the journey would be crushed at the singularity inside. This view began to change in the 1980s, thanks to a rather surprising source, the famous astronomer and science communicator Carl Sagan. Sagan was writing his science fiction novel, Contact, and he wanted a scientifically plausible way for his heroine to travel across the galaxy. So he did what any good scientist would do. He consulted an expert. He reached out to his friend, the brilliant theoretical physicist Kip Thorne at the California Institute of Technology. Sagan asked Thorne a simple question. Is there any way within the known laws of physics to create a stable, traversable wormhole? What Thorne and his team discovered was revolutionary. They found that a traversable wormhole was indeed possible, but it came with a very strange and demanding condition. To keep the throat of the wormhole open, to prevent it from collapsing, you would need to prop it up with a bizarre form of matter that has negative energy or negative pressure. This substance has been nicknamed exotic matter. The calculations performed by Thorne and other physicists suggest that to open a wormhole just 1 meter wide, large enough for a person to pass through, you would need an amount of negative energy equivalent to the total energy output of a vast number of stars over their entire lifetimes. The idea of negative energy might seem like a desperate trick to make wormholes work, but it actually has a surprising basis in real physics. The source is the strange world of quantum field theory and phenomena like the Casimir effect, which has been measured and confirmed in laboratories. If a wormhole can connect two different places in space, could it also connect two different moments in time? This question takes us from the realm of interstellar travel directly into the even stranger territory of time travel. The connection between wormholes and time travel arises directly from Einstein's theory of relativity. If you have a wormhole connecting 2 points, you have 2 mouths to the tunnel. If you took one mouth on a journey at nearly the speed of light and then brought it back, time dilation would take effect. You would have created a time difference between the 2 ends of the same tunnel. The wormhole has become a two-way gate, connecting 2 different points in history. A traveler in the year 3100 could enter one mouth and emerge from the other in the year 3001, traveling 99 years into the past. The moment you introduce the possibility of traveling into the past, you run into a series of famous and deeply troubling logical problems known as paradoxes. The most famous of these is the grandfather paradox. A time traveler goes back in time and causes their grandfather's death before he has a chance to meet their grandmother. If the grandfather dies, he can't have children, meaning the traveler's parent is never born. If the traveler is never born, they could not have gone back in time to kill their grandfather in the first place. This creates an unbreakable loop of contradiction. Faced with these paradoxes, physicists have proposed several solutions, from the Novikov self-consistency principle to Stephen Hawking's chronology protection conjecture, suggesting the universe may have its own ways of protecting the integrity of the timeline. While physicists debate the complex mathematics of exotic matter and the paradoxes of time travel, storytellers have embraced wormholes with open arms. In the world of popular culture, these cosmic tunnels are not just theoretical possibilities. They are essential plot devices, powerful symbols, and gateways to adventure. One of the most iconic examples is the television series Stargate SG-1, which built its entire premise around a network of ancient wormholes connecting planets across the galaxy. The Stargate franchise popularized the idea of a wormhole as a reliable transportation system, a kind of cosmic subway. More recently, the 2014 film Interstellar, made with the scientific consultation of Kip Thorne himself, brought a new level of realism to the portrayal of wormholes. The film depicted the wormhole as a calm, spherical distortion in space, based on Thorne's actual calculations. The constant presence of wormholes in our stories does more than just entertain us. It actively shapes our expectations for the future of space exploration. These stories keep the dream of interstellar travel alive in the public consciousness, ensuring that we continue to look up at the stars with a sense of wonder and ambition. The relationship between science and fiction is not a one-way street. Fiction can provide a sandbox for theoretical physicists to play in, creating a feedback loop where imagination inspires science, and science, in turn, inspires new stories. We have journeyed to the very edge of theoretical physics, through the warped fabric of space-time, and into the heart of cosmic mystery. So, what have we learned? What do we truly know about wormholes? The honest answer is that they remain, for now, a beautiful and compelling mathematical idea rather than a confirmed physical reality. They are a valid solution to Albert Einstein's equations of general relativity, giving them a solid foundation in our best theory of gravity. However, the gap between the tiny amounts of negative energy seen in quantum effects and the planet-sized quantities needed to sustain a macroscopic wormhole is vast, a chasm we currently have no idea how to cross. Despite all our progress, the wormhole remains one of the most profound and enduring mysteries in all of science. The central unanswered question is simple. Do they, or can they, exist in our universe? At this moment, we simply do not have the evidence to say for sure. The search for answers pushes us towards the greatest unsolved problem in modern physics, the unification of general relativity and quantum mechanics. To truly understand if wormholes are possible, we need a complete theory of quantum gravity, a single framework that can describe all forces of nature. Whether or not we ever find a real wormhole, The ones we have created in our stories have already taken us on an incredible journey. The wormhole is a powerful symbol of human potential, a testament to our ability to imagine worlds and possibilities far beyond our immediate grasp. The journey has just begun.